Good morning, class. We are looking at chapter 6, application of integration. And here's the last part, 6.4 work, 6.5 average value of a function. Integrals as net change. I hope you remember F equals ma, Newton's second law. M is the mass, A is the acceleration. Newton's second law of motion states that force is equal to the rate of change of momentum for a constant mass. Force equals mass times acceleration. The momentum of a body is equal to the product of its mass and its velocity. I am reminding you some basics from the physics. Work is the result of a force being applied to an object over some distance, which in turn may change the object's total energy. When the amount of force varies, we use calculus. Otherwise, it's just F times the W is F times the force times the distance. Hooke's law, which applies to a spring, capital F is K times X. F is the force and K is the constant of the spring. X, we used to use delta X in physics, the change from its natural length. That's what X is. And again, we call the delta X in physics in case, if you remember that. So K is the spring constant, newtons per meter, because in SI system, F is in Newton and X, the distance in meters, that the spring is extended beyond its natural length. When the amount of force varies, use calculus. Over a very short distance, even a non-constant force doesn't change much. So work becomes dW F of X times dx. Adding them up, work done in moving an object from point A to point B becomes a summation of F of X by delta X. And we take a limit as n goes to infinity. And as you know, this is the integral of A to B F of X dx. So W is the integral of A to B F of X dx by definition. So let's look at this example. What is the force or weight on the bottom of the aquarium? How much work is done if the aquarium is lifted to a height of 10 feet? Well, first, F equals ma. If it's weight, F equals mg, the g force. Work, W equals F times D when the force is constant. So in this case, the density, I'm reminding everybody, that is defined as the substance's mass per unit of volume. Rho equals m over v. Therefore, m is rho times v. That's the product of the two. I hope everybody remembers that again from basic physics. So the volume of this rectangular solid is the length times the width times the height. And the water has a density of 1,000 kilograms per cubic meters in SI system or metric system, or 62.5 pounds per cubic feet in the old British system, also known as US customary system. So it's a piece of information that should be given, okay? So they give you this information. Now we need to calculate the volume. So we multiply all the sides, 2 times 3 times 1. This is 6 cubic feet. M is rho times V. So we're going to multiply this by which one? Because this is cubic feet, we're going to multiply by 62.5 because it's using the old British system. And 62.5 times 6 results in the weight of 375 pounds. In the old British system, they call the M as weight. So W for part B, how much work is done, it's F times D, and the distance is given as 10 feet. So we have 375 times 10 makes it 3,750 foot-pound. This is the units of work for the old British system. The units of work for metric system is joules. 1 joule is 1 Newton times 1 meter. And Newton here, M times A, meters. M stands for the mass, kilograms. A is for the acceleration, meters per square second. And then another meters makes it meters squared. So if I were to write this for you, this, according to this, is M, the mass is in kilograms, times A, acceleration, meters per square second. So if you multiply this one by this one, you get these units. So Joule, unit of work or energy in the International System of Units, or SI, it is equal to the work done by a force of 1 Newton when its point of application moves 1 meter in the direction of action of the force. James Prescott Joule. It equals 10 to the power of 7 ergs, or grams centimeter squared per second squared, or approximately 0.7377 foot-pounds. These are all conversions, if you will. A spring has a natural length of 1 meter. A force of 24 Newton stretches the spring to 1.8 meters. Find the value of K, the constant of the spring. So let's see what happens. Let's write the given. So the natural length is 1 meter. The force of 24 takes it to 1.8. So L plus X becomes 1.8. So if we call L as a natural length, force of 24 Newton causes it to go to 1.8. So L plus X becomes 1.8. So it stretches it by 0.8. So it goes from 1 to 1.8. So the amount of X is 0.8, or 1.8 minus 1. We want to find the K. So you can think about it this way. L, the natural length without any force, is 1 meter. When we exert the force of 24 Newton, 1 plus X becomes 1.8 meters. Just Newton, okay? All right, so F equals Kx. So we replace the F with 24, K is missing, X. Take a look at this one, X is 0.8. Again, please understand, 1.8 minus 1 is 0.8. So let's write this as, and so divide both sides by 0.8, which becomes 240 divided by 8, or 30. K is 30, therefore F is 30x. By the way, as far as the units, this would be newtons per meter in case. How much work is done? How much work would be needed to stretch the spring 3 meters beyond its natural length? Well, we know F is Kx, which is 30x, and W uses this formula. And we're going to go from A to B, from 0 to 3, because 3 meters beyond the natural length. All right, so let's plug in. We're going to replace this with 30x. A is 0, B is 3, 30x becomes 15x squared, and if you plug in 3, 9 times 15, 135, 0 doesn't do anything, 135 joules. So it takes 135 joules of work to stretch the spring 3 meters beyond its natural length. If the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pound, A, find the value of K. So let's write the given. And by the way, that's Hooke's law that we needed. So the amount beyond the natural length is 1, so X is 1 foot. The amount of work is 12 foot-pound, and K is missing. So first, write the given symbolically anytime you're dealing with a word problem. So X is 1 foot. W representing the work is 12 foot-pound, and K is missing. So we write this formula, and A is 0, B is 1, because it says it 1 foot beyond the natural length from 0 to 1. So therefore, what is f of x? We don't have it. We're going to call it kx. From 0 to 1, it's equal to 12 when we take the integral. So the integral of 0 to 1 kx dx is 12 foot-pound. As you know, this is half of kx squared. If I plug in 0, it goes away. Just plug in 1. So I get 1 times k, or k over 2, or half of k, equals 12. And so k is 2 times 12, or 24 pound per foot. So F is kx. F is 24x. Therefore, we are ready to do part B. How much work is needed to stretch the spring 9 inches beyond its natural length? In other words, this formula, we have f of x, which is 24x. We have a equals 0. But what is b? B is 9 inches. Well, 9 inches means 9 over 12, or 3 over 4 feet. So you have to write it in this format. So your b, in this case, 9 inches corresponds to 3/4. So it's no longer 1. So that's really the key. All you have to do, be careful with your units. You have to use proper units. So foot-pound, this must be in, you have to change them in feet. And to do that, you divide the 9 by 12, because 1 foot is 12 inches. Okay, everybody knows that. And so this becomes 12x squared and you just plug in x equals 3/4, 0 makes it 0. So replace the x with 3/4. So 12 times 3/4 squared or 9/16 makes it 27/4. And the units are the units of the work in the old British system, foot-pound. Foot-pound. A 180-pound cable is 60 feet long and hangs vertically from the building, from the top of the building, top of a tall building, if you will, top of a tall building. How much work is required to lift the cable to the top of the building, to lift 25 feet of the cable to the top of the building? So let's stick with part A first. And even for part B, we do some of the stuff that are similar. So how much work is required to lift the cable to the top? We want to lift the whole cable to the top. The density rho is m/v, and the linear density, in this case, 180 divided by 60. That means every foot of this chain, this cable, is 3 pounds per foot. It weighs 3 pounds per foot. So now we have a tall building, 60 feet long. The purpose of a tall building is that, you know, it's taller than 60. That's the concept. Small piece of cable of length dx pulls down with the force weight of 3dx times pound. So if this distance is delta x or dx, when you multiply it by this, that gives you the force, which is ma, if you will. So that gives you the force, 3dx, because it's 3 pounds per foot. 3 pounds per foot times this much, this size, this distance of delta x or dx gives you 3 times dx, and the units of pounds per foot times foot becomes pounds. Let x be the distance of the piece of this cable from the top of the building, this distance of x. To lift this piece to the top, 3dx pound, up to the top. The work done is dw is f of x times x. Just remember, we have a varying force. Y is the force varying because it depends how much is left. If you have, let's say, taken 1 foot up, then 59 feet is left, and then 2 feet up, 58 is left, and whatever is left, the weight is different. That's why it's not a constant force, and that's the key. It is not a constant force. So we have 3dx times x. So I like to put the x in B4 dx, or 3x dx, foot-pound. That's an increment of the work. So the work is the integral of this from 0 to 60. Now, of course, this is 3/2 x squared. You replace it with 60 squared times 3/2, you get 5,400, and the units would be foot-pound. So the cable is 60 feet long. That's why from 0 to 60. Now, what happens to part B? We are going to lift only 25 feet. So we consider two parts. The top 25 feet and the bottom 60 minus 25. The bottom is 60 minus 25 or 35 feet. I want to make sure we understand why 35. 60 minus 25 gives us 35 feet. Now you can think of this as a fixed amount because this 35 feet, if you think of them as one piece altogether, they have to move up by 25 feet. So this is fixed, but this is not. The top 25 uses the same formula here, but from 0 to 25, because this has a variable force. The top 25, think about it. So if you cut this to the bottom 35 and the top 25, the bottom 35, the whole thing comes up. But the top 25, if you're at the top, let's say 1 foot, only 1 foot comes out. But here 2 feet and so on and so forth. So that's why this is variable. And therefore we use this formula again, 3/2 x squared from 0 to 25. Replace the x with 25 and square it times 3/2 gives you 937.5 and use the proper units, foot-pound. The bottom part is fixed, okay? So basically it is 3 pounds per foot. There are 35 feet. So the product of the two is the total weight of the bottom, and you bring it up by 25 feet. W is FD. I want to make sure we understand. W is FD. F in this case would be 35 times 3. And then the distance of bringing it up 25 feet. So I put rho VD. That's what I mean by that, okay? So 3 pound per foot. There are 35 feet. So this is the force weight of the bottom 35, which moves up 25 feet. So the whole bottom of 35 feet weighs this much, 3 times 35 in essence, and it comes up by 25 feet. The product is 2,625, and add them up. There you have it. Now, what's interesting, we can have a different approach, and I'm going to quickly explain that, and you can just calculate it on your own. And that would be the distance from the bottom of the cable is x. The force is proportional to the remaining distance to the top, which is 60 minus x. So if this is x, this is 60 minus x, okay? And so we still have this concept. This is not going away. But what happens is that the dw now, f of x dx, force times the distance, is 3 times 60 minus x times dx. So any of this, if the bottom is x, any part, any increment of this chain, this cable, at any distance from 0, from the bottom, which is x, has 60 minus x left to go up. So it's going to go up by 60 minus x. So 3 times 60 minus x dx. Now, to make sure this makes sense, we are going to look at x equals 0. When x is 0, that means starts from here, right? If x is 0, that means we have to move it 60. So that 60 times 3 is 180 pounds. But if it's 60, if it's all the way up, there's nothing to do. So take a look. This has to be checked. So at x equals 0, if you replace x equals 0, you have to get that 180 pounds because it weighs 180 pounds, the whole thing, right? So right here, it weighs 180 pounds. And remember, this is going to get, this value gets smaller and smaller as we get it up there, right? And it covers a different distance at any given time. On the other hand, at x equals 60, if you plug it in here, it's 0. That means when x equals 60, it's all the way at top. There's nothing to worry about. There's no way. So therefore, for the first part, so we use this one, but with this formula. And I'm going to leave it for you to verify it's equal to that. For part B, from 0 to 25. Now, which way you have a better understanding, it's up to you. You want to stick with that. Stick with the part that you have a better understanding and follow that and use the same methodology. Here's another example. A leaky 5-pound bucket is raised 20 feet. The rope weighs 0.08 pound per foot. The bucket starts with 2 gallons or 16 pounds of water and is empty when it just reaches the top. All right, so we consider 3 things. So 0 to 20, we consider 3 things: bucket, water, and rope. First, understand the bucket weighs 5 pounds. And it's always 5 pounds. I'm not talking about the water, just the empty bucket. So W equals FD. F is 5, distance of 20 feet, fixed. It's 100, 5 times 20, 100 foot-pound. So nothing changes. For the water, what's happening with the water that it's leaking? If the water was not leaking, it would follow exactly the same thing as this one. Whatever the weight of the water times 20 feet. But it is leaking, which means the water, the amount of water, and therefore the weight of the water varies as we go up until it becomes 0 at the top here. So again, the density, rho is m over v. The linear density is 16 pounds per 20 foot because the water weighs 16 pounds per 20 foot. That means 4/5 of a pound per foot. Again, the small amount, so this is delta x. The small amount of the water of length dx or delta x falls down with the force weight of 4/5 dx. So if we let x be the distance, it's going to go up. Let x be the distance of this part of the water from the top. To lift this part up to the top, it requires the force of the work of, if you will, dWf of x dx, force times the distance. And now we are going to integrate that 4/5 of dx times x, or 4/5 of x times dx, right? Because this distance is x. And so from a to b f of x dx, this is going to be from 0 to 20. Okay, 4/5 times half of x squared makes it 2/5 x squared. Plug in 20 squared times 2/5, and we get 160 foot-pound. That's the amount of work that we need to exert to take this all the way up. As far as the rope is concerned, it's exactly the same thing. It's just like a cable of the previous page, or just the water here. We have the same situation, so we have to find the density, linear density. So it is 0.08 pound per foot is given. The linear density is given. So force times the distance, and the distance it covers, it's x, so 0.08 dx. 0.08 dx is the force times the distance. That's an increment of a work. And we are going to integrate this from 0 to 20. As you know, it becomes 0.08 times half of x squared, or 0.04 times x squared, from 0 to 20. Replace the x with 20, and we end up with 16. And all we have to do, add those three values. 100 plus 160 plus 16 is 276 foot-pound. 276 foot-pound. Okay. Let me quickly look at the same question, but a second method. Again, we are going from 0 to 20, bucket. It has a fixed weight of 5, so 5 times 20 is 100 foot-pound. As far as the water is concerned, the force is proportional to remaining rope. That part works the same for the rope, okay? And so we write down 16 pounds over 20. Remember that we had it in the previous page also. We ended up with 4 over 5. I hope you remember. I don't want to, we went over, this is the linear density as we calculated before. At this time, we multiplied by 20 minus x. And when we simplify, becomes 16 minus 4/5 x. And so we can check it out. What happens at x equals 0? We get 16 pounds. We are talking about the water. We have 2 gallons. It weighs 16 pounds in the beginning. All the way up when it's 20 divided by 5, 4 times 4, 16. 16 minus 16 is 0. So it becomes 0. By the time it gets up there, it gets 0. So the formula works. So we're going to integrate this from 0 to 20. So this is 16x minus 4/5 times half of x squared, which makes it minus 2/5 x squared from 0 to 20. And you plug in 20, you do the math. You get the same value of 160 foot-pound. Now, for the rope, we follow exactly the same thing. The force is proportional to the remaining rope for this part. And this one is 20 minus x, just like this one. But instead of that, we're going to write times 0.08. You can put it in the front or in the back, it doesn't matter. So you're going to distribute that, and it will give you the simplified version in a moment, which is 1.6 minus 0.08x. But to check it is easier. If you go with a 0, you get 1.6 pounds. And if you go with 20, you get 0. So you can see that it works. We are going to integrate that from 0 to 20. So this gives us 1.66. By the way, this been distributed. Okay, 1.6 x minus 0.08 times half of x squared, which makes it minus 0.04 x squared. And evaluated from 0 to 20 gives you the same 16 foot-pound as before. Now add them up, you have the answer. Now, you can also write the whole thing in one shot. The integral of 0 to 20 and add this to this to this. So the integral of 0 to 25, then 16 minus 4/5 for the water, 1.6 minus 0.08 x for the rope, dx. If you integrate this one in one shot, you get the same answer. All right, the last topic is the average value of a function. So I'm reminding you that in order to find the average, we add up the sum divided by n. That's how you find the average, right? Now let's take the average over infinitely many values. For example, when you have a function, you have infinitely many values, right? So how do you take the average of the functional values, right? There are infinitely many. Well, the f average would be f of x sub 1 plus f of x sub 2 all the way to f of x sub n divided by n roughly. The reason we have an approximation because this has to go indefinitely. Okay, so that's f of average. Now, we want to rewrite this. To rewrite this, we're going to rewrite the n. And the way we do that, remember that delta x was b minus a over n. So we can interchange this to n becomes b minus a over delta x. And therefore, this is 1 over n, right? 1 over n times f of x up 1 plus f of x up to all the way. So 1 over n would be the reciprocal of that. Please understand, 1 over n times this. So the reciprocal of that, delta x divided by b minus a times this. Now, this one, we can write the summation of f of x sub I. We can put the delta x in. Please understand, this is the summation. This is this part. And I can, delta x is a fixed number, is a constant. I can take it in or out, makes no difference. I can even take b minus a inside, but I don't want to do that. Why is that? Because I want to remind you that this was the fundamental theorem of calculus, the integral of a to b f of x dx, one of those FTCs. And so what happens is that when you're looking for the average of the function, and of course you're dealing with the continuous function, there is some value in between. So the f average, it so happened to have two functional values having the same average. What you need to know, is extremely important, the area of this rectangle, which is b minus a times f average, is equal to the area, the total area under the curve. If you look at this, just do the cross product. If you multiply b minus a by f average, b minus a by f average, b minus a by f average is the area of the rectangle. What is this one? Without 1 over b minus a, for a continuous and a positive function, that's the area under the curve. Find the average value of the function f of x equals x squared over the interval of 0 to 2. And we know here's the f average equation we should know. So let's graph the function. This is y equals x squared. We're going to go from 0 to 2. So we are interested in the average here. And ultimately, there is some point that if you draw a rectangle, the area of that rectangle becomes the same as the area under the curve. That's the concept. So from 0 to 2, a is 0, b is 2, 1 over 2 minus 0, f of x is x squared. Just simply plug in. This gives you 1/3 x cubed. 1/2 and 1/3 is 1/6, or you just write 2 cubed. 0 doesn't do anything. So 2 cubed over 3, and that makes it 8 times 1 is 8, 3 times 2 is 6, 8 over 6 or 4/3. 8 over 6 or 4/3. This is 8, everybody. So f average is 4/3. So there is some point, and by the way, we can figure out what that is. If we set this one equal to 4/3, we can find the x coordinate of this point. So this point has some x coordinate, which we haven't found. But here's what you want to know. The area of the rectangle, again, which is b minus a, in this case 2 minus 0, times f average. So b minus a is 2, and f average, we found it to be 4/3, it's 8/3. So this rectangle has the area of 8/3. The area under the curve is also 8/3. If we are interested in finding at what point this is the case, then all you have to do, say x squared equals 4/3 and so on. Needless to say, it gives you two answers, positive and negative. You keep the positive one, as you can see from the graph. Find the value c guaranteed by the mean value theorem for the integral for the function of f of x equals x cubed over 0 to 2. Well, here's the f average, 1 over b minus a, the integral of a to b f of x dx. They are looking for the point that I mentioned in the previous case. So we want to find the x coordinate that gives us the average. So first and foremost, we are going to replace the a with 0, b with 2, and f of x with x cubed. And of course, let's graph it. So here's the graph. We want to go from 0 to 2. So this is the portion of a y equals x cubed over f of x equals x cubed we are interested in. Now this area, we can find it, and this area is equal to the area of some rectangle with the width of 2 minus 0, which is this one, and the height of this f average we're going to find. So let's plug in. This becomes 1/4 x to the power of 4. If you plug in 2 to the power of 4, 16, divided by 4 is 4, times 1/2 is 2. So the f average is 2. Please understand it means 2 times this is this one, which is the area under the curve. So f average is 2. So what is this equal to? 2 times 2, 4. So what you want to find, if the f average is a 2, you set f of x equal to that to find the x coordinate for that point. So there is, so somewhere that this f average exists, and remember, this is 2, right? The average is 2, so 2 and 2, okay? 2 times 2 is 4. The area under the curve is 4. The area for the rectangle is 4. We write f of x equals x cubed equals to the f average. And x becomes the cube root of that. Again, this is a precise answer. You can always use a calculator to see what you have, a rough estimate, but we rather use the exact answer. Okay, everybody? It's about 1.25 or something. Okay, so this is about 1.2599. So this is roughly 1.26, just to give you an idea. So this point has the exact location x equals cube root of 2, which is about 1.26. See, 1.26. And the y coordinate of 2.